Welcome to the Electronics Engineering Bootcamp, Beginner's Basic Electricity. This video lecture will explain the basics of resistance and answer some questions regarding what is a resistor, how does a resistor work, how do series and parallel combinations of resistors affect resistance, and what are some common applications. Resistance is the measure of how well a material resists the flow of electric current. It has an SI unit of ohm and denoted by the Greek letter omega. This diagram is an excellent representation of how voltage, current, and resistance work together in a circuit. Voltage pushes electrons to create current, while resistance limits its movement. This is the US and European schematic symbol for a resistor. In a typical circuit drawing, all resistors will have an accompanying name and value. Resistors come in many shapes and sizes. The size of the resistor typically determines the wattage, or how much heat it can dissipate without burning. From right to left, a 1/8 watt, quarter watt, 1 watt, 5 watt, 10 watt, 20 watt, and so on. The value of the resistor is typically either color-coded or written directly on its surface. Through-hole resistors contain 4 or 5 bands of varying colors that describe the amount of resistance and tolerance for each resistor. From the table to the right, the first and second bands represent the first and second significant digits. The third band represents the base 10 multiplier, and the final band represents the typical tolerance value. For the 4-band resistor above the chart, the first band is green, giving us a value of 5. The second is blue, giving us a value of 6. The multiplier is yellow with a value of 10 kilo-ohm, and the tolerance is gold with a value of 5%. Putting all the numbers together gives us a resistor value of 560 kilo-ohms with a tolerance of plus minus 5%. Resistance depends on 3 properties: the diameter of the conductor, the length of the conductor, and the material of the conductor. The diameter of the conductor limits the amount of electrons that can pass through. The conducting material also affects its resistivity. Different conducting materials will have different densities, lattice structures, electron affinities, and other factors that come into play. For simplicity, density is used to show how different materials can have more or less electron collisions as they pass. The third method is by controlling the length of the material. An electron traveling through a longer conductor of the same material will interact with more atoms, losing more energy in the process. Using these 3 methods, manufacturers manipulate the material, diameter, and length of the conductor used in resistors to achieve a precise resistance value. The total resistance of resistors connected in series is the sum of their individual resistance, while the total resistance of resistors connected in parallel is the reciprocal of the sum of the reciprocals of the resistors. For example, putting a 100 ohm and 5 kilo-ohm resistor in series, the total resistance as measured across the terminals A and B is 5.1 kilo-ohms. Connecting a 100 ohm and a 5 kilo-ohm resistor in parallel, the total resistance becomes the inverse of the sum of the inverses and results in 98 ohms. A good way to remember parallel resistances is that the total resistance is always smaller than the smallest resistor in the parallel chain. Resistors are commonly used to adjust signal levels, limit current, divide voltages, generate heat, bias active elements, and terminate transmission lines. We will only cover the first 4 applications in this course, while the remaining applications to be discussed in future courses. The most common use of resistors is to limit current. For example, connecting an LED to a 9-volt battery will draw the maximum current the battery can supply and damage the device. By putting a 220 ohm resistor in series, the current is limited to a level that is tolerable by the LED. Another common application is voltage and current division, and this is accomplished with series and parallel resistors. 2 similar valued resistors in series connected to a DC voltage source will output half the source's voltage in the middle. Generally, the voltage output of a divider is equal to the value of the bottom resistor divided by the sum of all the resistors in series and multiplied by the total voltage across the entire divider. If we increase the resistance at the bottom relative to the top resistor, the voltage output will increase. If we decrease the resistance at the bottom relative to the top resistor, the voltage output will decrease. Voltage dividers are useful for providing a constant voltage signal that is a fraction of the input voltage. Potentiometers are variable voltage dividers. The voltage division ratio can be adjusted by turning a knob. It has this schematic symbol containing 3 pins, representing the top and bottom contact of the resistor divider and the center output between the resistors, called the wiper. If you apply a voltage across the first and third pins, turning the knob will vary the voltage on the center pin. A potentiometer achieves this using a resistive track and a metal wiper that contacts the track. As you turn the knob, the equivalent voltage divider ratio changes, varying the output voltage. Potentiometers come in a variety of shapes and sizes, and are used to adjust signal levels in many familiar devices, most commonly the volume controls in audio equipment. This concludes the video lecture on resistance.